This problem is from chapter 23, number 11, a simple circuit. And it says, for a circuit of one light bulb of resistance 4 ohms and a voltage source that provides 6 volts, compute the power output. And then part B is, for a circuit of one resistor with resistance 50 ohms and a voltage source that provides 100 volts, compute the power output. Okay, so here's the first circuit, part A. Got a light bulb here. And let's see, I'm going to have a power source here, and then I'm going to do the wiring. There we go. And if I hadn't made a gap there a moment ago, I would actually have a closed circuit. There we go. Alright. So, in order to figure out what the power output is, power equals current times voltage. I would need to know what the current is. I know what the voltage is, given as 6 volts. So I need to know what the current is. Well, the current I get from Ohm's law in the form of the current equals voltage divided by resistance, which then is given as 6 volts divided by 4 ohms, and that is 1.5 amps. And then I plug that in here. Power equals current times voltage, so 1.5 amps times 6 volts, and that comes out to 9 watts. Okay, the second part is virtually the same. The calculations are really virtually the same. I'm going to see if I can just copy everything here and carefully pull it down without losing anything, and then just fix a few things, such as this will be our problem B, and I have different numbers here on the second part. And of course, in this case, I do have a resistor. I'm going to take this out here. And we'll draw in the resistor. And there's the wire. And then I will write on here 100 volts. And this one here is 50 ohms, which actually in the last problem I had forgotten to write on. Always makes it look a little better and more complete when we write those designations on there. Any case, same calculations here. Current equals voltage divided by resistance, so 100 volts divided by 50 ohms equals 2 amps or 2.0 amps. In these kinds of problems, we assume that these are exact numbers, that really 100 volts is applied to an exact 50 ohm resistor, each one of them with just a small error. So that's why I go out to significant figures here. Should have done that over here too. That should be 9.0 watts. Okay, and then so I have 2.0 amps here, and I multiply that with 100 volts, and that equals 200 amps. Oops, 200 watts. Okay. There are a couple of follow-up problems that will be more complicated. The first follow-up problem will be a series circuit with several elements, several side light bulbs or resistors, and then the next problem will be a parallel circuit, also with several light bulbs, respectively several resistors. So we be calculating more along the same lines, making it a little bit more complicated. But before I go there, I figured I'm gonna actually show you a simulation applet. So here we go. This one here is from PhET, P-H-E-T, Physics Education Technology. And I'm going to grab a light bulb, and if I remember correctly, that light bulb has a resistance of 4 ohms. So there we go. Show value 4 ohms. I'll put a wire on this one here. I'll put another wire over here. And might as well use a switch. Could have used that on the other one too. Apparently I have to pull on the joints. I'm going to put an ammeter in here. And I need another wire to connect. There we go. And yet another wire there. And I need a battery. There we go. And it's at 6 volts on the first one. So 6 volts. Show the value. There we go. It says something about internal resistance. For our calculations, it would be good if we just had 0.0 ohms internal resistance, but I'm going to put 0.01. Oops, that was interesting. I will put 0.1 ohms because it's more realistic. The battery itself is actually also drawing a current and using up power. That's why when you short circuit a battery, the battery will heat up because it's using up its own power. Okay, the circuit is closed, except I still have to close the switch. And here, keep in mind how bright they make this light bulb here as we go later to the parallel and series circuits. So keep in mind how bright this one actually is. I don't think I can move everything at once. No, I really can't. Look at the current here, 1.46 amps. It's not exactly 1.5 amps as calculated, but that's only because I put a little internal resistance in here. So this one here is actually around at 1.5 amps, which is the same thing as the problem was. Again, if I change the internal resistance here on the battery itself, I do come up with exactly 1.50 amps. But this one here is more realistic. Okay, and then of course 1.46 or 1.5 amps rounded times the 6 volts on the battery, that comes out to the calculated 9 watts. Okay, now the resistor. So I'm going to put a resistor in here. There we go. Okay, and it says in there that it's a 50 ohm resistor. And the battery is now supposed to be 100 volts. That's quite a battery. And close the, oh yeah, show the value here. There we go, 50 ohms, close it. And I come up with 2.00 amps, even though the battery has some internal resistance. It's so small compared to this 50 ohm resistor that it really doesn't affect the current. So it's really the resistor that is using up the power. And so, just as calculated before, 100 volts divided by 50 ohms is 2 amps. And then 2 amps times 100 volts is the 200 watts that are being used by the resistor. In this case here for this applet, it doesn't show the calculation for the power, so we still have to do it, but that's really easy. 2 amps total current times 100 volts for the power, which makes 200 watts.